So the quiz tomorrow is going to cover um, a few things. First, parts of the atom. So we've talked about um, the basic construct of the atom, and you've drawn diagrams of them, and I'll do another diagram here just to go over that with you so that you're clear on that. So parts of the atom. The second thing that the quiz will cover is the basic ideas that are related to the rotations that you did in the back. So one of the main ideas is that atoms are very small. So atoms are extremely small. A second idea is that this whole idea of empty space. So we did a couple of simulations, or actually we did the human hydrogen atom model, in which we increased the size of the atom on two different scales. And what we found is that there is a lot of space inside of the atom. So in general, matter is mostly empty space. Okay? So matter is mostly empty space. And then I would say the third idea is this whole idea of big and small being very relative. Big and small are relative terms. Okay? Because when you just think back when you saw Cosmic Voyage, the video you saw last week, and then also at Station 6, the interactive that you and your group worked through, Scale of the Universe. You saw the smallest of the small to the largest of the large. And any of those items, we could look at them and say that one is larger than another, but then there's always something else that's larger than what we thought was big in the first place. So it really just depends on what items are being compared and your perspective. So big and small are very relative terms. As far as parts of the atom go, let's draw out a diagram of the atom. So here's what I'd like for you to do. On a sheet of paper, I want you to draw what I'm drawing. And of course, this is not to scale. All right, and what I've drawn here is the helium atom. And I've drawn helium because I know it has both protons and neutrons, instead of drawing hydrogen, which only has protons but no neutrons. All right, so if we were to label this atom, if I were to ask you to label it, how would you do it? Go ahead and take a minute and do that now. And I also want you to label, I'm going to blow up one of these. I also want you to label what's inside of a proton and what's inside of a neutron. So we're magnifying those. Sorry, my circles aren't very perfect there. So go ahead and draw it, and then I want you to label it. Okay, so at this point, you should have it labeled. So let's see if you were correct. So these structures we're going to call electrons. And I forgot to ask you to put in the charges. So the charge for an electron is actually negative. And in terms of the amount, the charge is -1. So put a -1 by that. Then, of course, this is an electron as well, so it's going to be a -1 also. All right? So inside of the nucleus, we have protons and neutrons. So I'm going to call these two protons. And then these two are neutrons. Helium has 2 protons, 2 neutrons, and 2 electrons. I'm going to write that up here. Okay, 2 protons, 2 neutrons, and 2 electrons. So we're going to call the purple ones are protons, and we're going to call the green ones are neutrons. Okay? Protons have a charge of +1, and neutrons, if you said no charge or 0, then you're correct. Now, I drew these circles as magnified circles because I want us to show what's actually inside of a proton and what's inside of a neutron. So let's start with the proton. So if you said there are quarks inside, then you are correct. And if you drew 3 quarks in there, then you're also correct. But did you draw the correct quark configuration? If this is a proton, then we should have 2 up quarks and 1 down quark. Okay? Let's go to the neutron. A neutron should also have 3 quarks. And as far as the configuration, you should have 2 down quarks and 1 up quark. Now, what if you were asked to justify why protons and neutrons have the charges they have? Or why a neutron has no charge, rather. Then what could we say about the charges for the quarks? If we're dealing with a proton, we have 2 up quarks and 1 down quark.
So just know that he was
Sorry about that. Where was I? I was probably talking about the proton. So if you were asked to justify why the proton has a positive 1 charge, then you would need to add up the charges for the quarks. So up quarks we know have a charge of positive 2/3. So there's an up plus another up quark plus a down quark here. So if we have 2/3 plus, and this is positive, plus 2/3 plus negative 1/3, when we add those together, we should get 1, positive 1. Okay, so that's going to be our charge for the proton, and this is how we get that charge because the quarks have fractional charges. Now, if we go to the neutron, can we, in the same way, justify why there is no charge, which is a 0? Well, we have 2 down quarks, so down plus up. So the down quark is minus 1/3 plus a negative 1/3 plus positive 2/3, and if you add those together, you should get 0. Okay, which means that neutrons will not have a charge. Okay. All right. So that's it for the parts of the atom, at least for right now. As we go forward, as we move forward next week and beyond, of course you'll learn more. But that's it basically for now. All right. So going back to the station activities, you'll want to make sure that you know which stations emphasized each of these points. Okay, you'll want to make sure you know which stations emphasized each one of those points. Now, can you think about which stations that you saw or rotated through the other day might have emphasized the point that atoms are extremely small? Now, definitely, I would say station 1, cutting paper to protons, and I know we talked about that one. Many of you got to around maybe 18 cuts, maybe 20, before you found that it was too difficult to cut the paper anymore. And I think we said that it would take about 60 cuts to get to an atom, and 90 cuts to a proton. Okay, so and there's no way you can do that with the scissors. So this helps us understand that atoms are extremely small. I would say that station 2 emphasized this idea that matter is mostly empty space. That was with the lens paper. So as you zoomed into the lens paper, you saw lots of open space there, and we weren't even at the atomic level. And you saw lots of space, not only outside of the fibers, but also within the fibers. So definitely, station 2 emphasized that point. Station 3 was all about modeling. About modeling the atom. Station 3 was about modeling the atom, and we just went over that. Station 4 at Station 4 you saw 2 videos. One was dealing with how small the atom was, and then the other, I think both were dealing with how small the atom was. Really, I told you that the first video was probably the most important. So the station 4 dealt with size. And station 5, this was a model, a simulation in which you were modeling the size difference between a proton and an electron. And so the whole idea was that if you were to increase the size of an electron to be the size of a bead, so if one bead equals one electron, so if one bead equals one electron, how many beads would we need in order to make a proton? And on your sheet, it tells you that I think it's 1,836. So 1,836 beads equal one proton. And then, of course, as I talked to many of you, it wasn't very practical to stand and count out 1,836 beads to make a proton. So we did a little conversion and converted the bead number into mass. So if one bead is 0.2 grams, 0.2 grams, then you had to do a calculation in which you had to figure out what number of grams would 1,836 beads be. And if I remember correctly, I think you found that that number of grams was 367.2 grams. And so at the end, you had to measure out 367.2 grams of beads, and then you could hold that container of beads and get a feel for the mass of a proton as compared to the mass of an electron, which would be one bead. And then finally, station 6. Station 6 dealt with scale. So you were able to look at measurements as small as a Planck length to things as large as, the entire universe. And you could make comparisons between things that are large and things that are small, and get a better understanding for where we are in this whole mix. So I think that's it. If you have any other questions, please feel free to come in and see me. I'm here during lunch. I'm here after school today. I'm here tomorrow morning. Please feel free to drop by. Your quiz tomorrow is very, very short. It might consist of a diagram that you have to label, perhaps similar to this, and about 2 or 3 multiple choice questions that relate to what you've done at the 6 stations. Okay, take care.